Want to introduce them?
We should. That was
Want to do an introduction, Chris? And then we're going to
All right. All right, it's projecting then. All right, so I was given the task of talking about soft collinear effective field theory and TMD evolution. As I was preparing these talks, I realized that there might be a definite maybe between those two, because you could spend a lot of time on either. But given my biases and the fact that we've been talking about TMD so much, I thought I would just focus on SCET and SCET's approach to factorization. And before I even get to SCET, I'm going to talk about something that has absolutely nothing to do with TMD physics. But that's just sort of to motivate the thinking of EFT thinking. And so what is EFT thinking? And when I say EFT, I mean effective field theory. First, you're going to decide that there's some degrees of freedom that make up your system. And you're going to figure out what those degrees of freedom are. Next, you're going to figure out what redundancies are in those degrees of freedom, or what symmetries they should obey. And finally, and this is probably the most important ingredient, is a concept called power counting. And power counting actually is a concept that is more than just trying to figure out what parameter is small, but it's finding out which parameter is small for the specific state of affairs or situation that you're interested in. So you can have a theory and you can have the same degrees of freedom with the same symmetries, but depending on what you're interested in, your power counting is going to be radically changed, and you're going to get very different EFTs, even though the underlying degrees of freedom and symmetries are identical. And so sort of illustrate EFT ways of thinking and sort of put meat on these 3 points, I'm going to talk about a very simple example that we all know and love. And that's the example of jelly. And I'm going to derive for you right now the EFT for jelly, and I'm going to derive for you the EFT for jelly using degrees of freedom, symmetries, and power counting. And hopefully I can go fast enough that it won't distract us too long, but we'll figure out something non-trivial just using those 3 things. And so the question is, what is jelly? Well, jelly is this weird amorphous tangle of proteins or starches, and trapped in those proteins and starches is water, sugar, and of course, delicious flavor. What is important about jelly is that it's amorphous on microscopic scales. So there's no preferred direction. Everything is just a randomized jumble. So we have to go through our EFT way of thinking, and if we're going to derive the EFT for jelly. And the first question is, what is our degrees of freedom? And you should think of these as the degrees of freedom on some mesoscopic scale. So we're not going to be looking at this microscopic scale that I drew of entangled starches and whatnot. Instead, we're going to think about, some big lump of these entangled starches and some sort of unit of jelly that's going to be abstracted. And we want to figure out how this unit of jelly, or this jelly element, is going to, what is its dynamics? So our degrees of freedom will simply be a set of scalar fields that depend on space and time. And you should think of these scalar fields as like the co-moving jelly element. So what do I mean by that? Well, what I mean is an I is going to equal just our space-time, our spatial dimension. So if we're in D space-time, then I just ranges from 1 to D minus 1, and those are just, you should think of them as sort of pseudo spatial coordinates. then our jelly elements at our initial time, we'll make this a vector. It's just where it is. And that's sort of what our jelly elements are describing for us. At time t equals 0, the jelly is just the jelly element at x vector. And then at later times t, this phi is sort of telling us how the jelly element at x vector displaced away from where it was at t equals 0. So this would be our initial conditions. Now, what is the symmetries of our degrees of freedom? These little jelly elements, sort of the coarse-grained mesoscopic scale element. Well, our symmetries are pretty simple. What we care about is displacements. So that immediately implies that there's going to be a translation symmetry. In other words, I could have taken my jelly element and I can displace it by an arbitrary translation. That's just fixed. In other words, the initial labeling that I did at some initial time was arbitrary. I could have come up with a different coordinate system and relabeled everything. It doesn't matter, because all I care about is the displacement of a particular jelly element from where it was at time t equals 0 to where it's going to be at time t. So I have a translational symmetry. Now, the jelly was sort of a randomized jumble at sort of microscopic, mesoscopic scales, which means there's no lattice structure. And I therefore have rotational symmetry. In other words, I can take any particular jelly element and I'm free to map it under some rotation to a new jelly element where this R is just a member of my rotational group for space. And finally, because we're high energy physicists, I'm only interested in relativistic jelly. And any non-relativistic jelly, I would just get some limit of expanding as the speeds go to 0. So from my degrees of freedom, I can build invariants. And this is sort of the most important thing about symmetries, is that once you have your symmetries, the only thing that you should be thinking about are the things that are invariant under those symmetries. So the degrees of freedom I initially wrote down, they're clearly not invariant under those symmetries, right? I can translate them and I can rotate them. So from those degrees of freedom, I need to build invariants. And once I have my invariants, then I will express anything that can be physically measured. And my dynamics in terms of these invariants. So what is the invariant that I need for jelly? And am I going too fast? Well, I'll introduce a particular matrix. Now, I've taken derivatives here, and so those derivatives will kill any translation that I make. So automatically, when I've put these derivatives in place, I've taken care of my translational symmetry that my jelly had. I've contracted my Lorentz indices of my derivatives, so now it's Lorentz invariant. And like I said earlier, these are scalar fields, so they don't have any transformation properties under the Lorentz group. The only thing I have left to get rid of is just these free indices I and j, in other words, the rotations I could do on my jelly elements. But that's pretty simple. You just start taking traces of this matrix B. So that would be a particular invariant. And actually, I can come up with a whole set of invariants. So I'll label this X1, all my invariants are xk trace of b raised to some kth power. And I want xk and x1 to be sort of the same order. So I'll just divide out by trace of b to the k minus 1. That way they have the same dimensionality. All these x1s, xk. And because I have a rotational group d minus 1, you have what? SOD minus 1, I believe there's d minus 1 Casimirs. So that's going to tell you that you have d minus 1 of these x's that you can form that would be considered independent. So those are a complete set of invariants that I need. Now I've gone through my degrees of freedom, I've gone through my symmetries, and now I can write down an action for any jelly. Where F is smooth and sufficiently bounded on my jelly configurations. And there might also be some positivity requirement for F, but we're not going to worry about that. Now, you should all tell me this action is completely useless. And you're right, this action is completely useless. Because if I look at the space of functions, F, sufficiently smooth and sufficiently bounded for my physical jelly displacements, then that means I have an infinite dimensional space of possible actions that I could write down. Now, if I was a guy in Silicon Valley, then I would think, oh, high dimensional space, I should do some machine learning algorithm, perform big data. Get infinite experiments. And find out what my F is for some particular jelly. Maybe come up with some neat neural net representation of my F. I'm not in Silicon Valley. Somehow I wound up in Lannel. So I'm not going to do that. Instead, I'm going to use power counting to simplify my life. Now, we can go back and look at what our initial condition is, right? I just sort of said, wherever there is space, there is some particular jelly element. Jelly is everywhere and it is delicious. This will actually sort of inform for me what I'm really interested in, which is only small displacements of jelly. I'm interested in how jelly jiggles, not how jelly flows. Which means the ground state, or the state of affairs that I'm particularly interested in, is not just the initial condition that phi equals x vector, but actually phi equals x vector for all times. This would be my ground state. But I do want to have some dynamics. And so I'd be interested in small displacements away from my particular ground state. So pi vector, which is some small displacement. And what do I mean by small displacement? I mean that any derivative of my phi vector is very small compared to 1. And you can go through the dimensions and that works out, right? I'm taking a derivative. Pi has dimensions of length, and so the derivative of pi is a dimensionless quantity. So this is a good power counting quantity, and this is actually what I'm particularly interested in. When you go back to our particular action, we formed it from these invariants, and I can expand those invariants that I wrote up earlier by substituting in this x vector plus pi under this particular power counting, and there'd be some constant term. You can figure out what it is if you really want to. I'm going to break up my spatial derivatives and my time derivatives now. And I'm allowed to do that breaking up of spatial and time derivatives because I got this ground state that I'm expanding around x vector. So it allows me now to play fast and loose with my internal indices that I originally had and my spatial indices, my true spatial indices. There'll be a time term. There'll be this transverse term. You'll see why I call it transverse in a little while. And finally, there's quadratic in the divergence. And then there's higher order terms that are of order pi cubed. I'm not worrying about those. Now, the exact values of this A, K, B, K, C, K, D, K for each one of those invariants that I wrote up earlier doesn't really matter. All that matters is that they're all different. They're just different numbers. And you can go and you can calculate them. That'd be a wonderful exercise for you to go do. The important point is that I have basically two different structures. I have this divergent structure. I have this time derivative structure. And then I have sort of this, what I call the transverse structure. Like I said, I'll tell you why I really call that the transverse structure later. And now, when I expand my action, since these are the only three structures that I find, when I expand the action in this power counting that I wrote down earlier, I'll have some particular constant. I don't care about constants in an action. I'll have my time derivatives. I can get rid of any coefficient on front of those time derivatives by rescaling my action. So I'm not going to worry about what those are. Total derivatives, I don't care. So anything that's linear in the divergence, I don't care about. Just throw them away because they only are sensitive to boundaries and nothing lives at the boundary. And so the only other things that you can get is some term that is sensitive. It looks like this. And then my divergence term. And that's my action. Yeah, that fits, doesn't it? Now, I initially started with an F that lived on some infinite dimensional space, and it looked horrible and it looked nasty. I did this expansion once I had my power counting, and I realized all I really care about are small displacements. In other words, how the jelly jiggles. And now I find I really only have two constants that I need to worry about. This CT squared and the CL squared. What do the CT squared and the CL squared stand for? Well, that's going to be the speed of sound for any transverse wave moving through my jelly. And the CL is the speed of sound for any compressional wave moving through my jelly. To see that, all I have to do is split my pi field into some longitudinal component, into some transverse component, and I make this demand. Which I'm perfectly allowed to do. And then using this particular action up here, I can write down my two equations of motion.
Sorry, I didn't understand that command.
This,
Oh, you're requiring.
yeah, I'm just,
I see what you're saying.
I'm just introducing a longitudinal field that
Yeah.
sucks up all the divergence. And then I have a transverse field that has no divergence whatsoever. So I mean, this is really just an identity. I'm always allowed to do this, right? Assuming that I know how to solve Poisson's equation, I guess. So as long as I paid attention in undergrad math methods, then I know how to do this. So you all should have paid attention in undergrad math methods. T squared there. And I'll have a wave equation for my transverse modes. And then I'll have a wave equation for my compressional modes. So what has this told me? Well, the power of power counting has told me that I really only need to perform 2 experiments in order to figure out everything I would be curious about with my jelly. I should take my jelly and I should jiggle it on some platform. In other words, only excite transversional modes. And I should take my jelly and do what any kid would do with jelly and poke your finger into it in order to excite the compressional modes. And by making measurements on my poking and my jiggling, then I'll be able to find out what my 2 speeds of sound are, and I won't need any sort of fancy machine learning or anything like that. Now, why did I go through that exercise? Well, it's to show you that in order to make my effective field theory useful, I needed all of these ingredients. I needed my degrees of freedom, I needed my symmetries, and I needed my power counting. If I remove one of those pegs, then my effective field theory is not going to be very useful. But when I have all 3 of these together, I can just do some very naive reasoning, and I can come up with the EFT for jelly. Well, too far. And so that's, I don't know, I think that's pretty cool. And there's my jelly. Now, we're not actually here to study jelly. We're here to study QCD. Yes.
I know S squared is the real level function. So sign minus. Are there some reasons?
Oh, why are those minus signs in the expansion? Originally, those are going to come from the difference between your Lorentz, like, right? I split things up in terms of time derivatives and spatial derivatives.
Yeah.
And if you follow through the logic, then d squared goes as this, right? And all of these minus signs eventually come from the fact that I had a minus sign here. And earlier I said there's some positivity requirements on the F's that I wrote down earlier. Well, actually, if you go through what I really blasted through very quickly, and you figured out what these AKs, BKs, CKs, and DKs are, because they're just numbers fixed by the definition of XK, then you plug everything up into the F's. These CTs and CLs will have some definition in terms of that F and its derivatives. I mean, it's just constants, but you can calculate what it is. And that will turn out into a series of positivity requirements on those derivatives. Yes, it's some condition on F, because I know that I should get waves, right? I mean, that's just sort of physically, that's what makes sense. If I had a minus sign here, then I would get very ill-behaved solutions to my wave equations. I don't want that, right? And so that's sort of a physics fact that I would use. You can go through those exercises. You can get the speed of sound in terms of CT and CL. Those speeds of sound in terms of my F and its derivatives evaluated at where I'm expanding around. And you know that those should be sufficiently positive or coming with the right signs such that I get physical wave solutions. But I elided over all of that and I went ahead and put the minus signs in there because I know the speed of sound squared should be positive.
Yeah, so you introduced this notion of power count.
Yes,
So what you've done is to do a small, expansion around the ground state.
yes.
Where is the power count? Where, or maybe it's better to wait till you do stuff. But
So
Basically, graph pi is less than 1.
yeah, so the graph
Okay.
right there, that's my power count.
Which is just a small expansion.
It's just a small expansion. I'm saying that I'm only jiggling my jello slightly. So there's no large gradients,
Right.
which physically makes sense. If there was large gradients inside my jelly, I would soon not have jelly.
So you've got 0 limit.
You could. Well, no, the zero modes are kind of, I'm not going to be sensitive to those, right? Because of my translational symmetry, right?
Yeah, okay.
I don't care about total displacement.
That's why I understand what you meant by power count.
Yeah. No, this is a very good point. This is a very good point. And the important thing about power counting is that I have some ground state, and I'm only interested in small departures around that particular ground state. And when we form our EFT for QCD, so which will be soft collinear effective field theory, there'll be a particular momentum configuration that I'm interested in. In other words, your Born configuration. And you are only interested in small departures about that Born configuration. And when we demand that, that's going to inform us what our power counting should be when we get to QCD. Right. And it's not until we impose that we're actually going to be able to build anything predictive. In other words, we're going to go through the degrees of freedom. We're going to go through the symmetries. And we're going to find that we can write down all sorts of things. And most of it is useless until we impose some form of power count. All right, so now that we're all on page with sort of the foundational principles of EFTs, because now we know how to build the EFT for jelly. And if you want to know more about the EFT for jelly, then there's a fun paper to read. Where they propose the EFT for jelly to actually be a model of inflation. They're high energy physicists, what can I say? It's still fun to read about the EFT for jelly. So now in QCD, we're going to go through the exact same logic. In QCD, we're aiming for a particular EFT of QCD, which is soft collinear effective field theory. Note, when I write down the degrees of freedom and my symmetries, from these two alone, there's all sorts of effective field theories that I could write down. There's QCD itself. There's NRQCD, which comes in all sorts of flavors. There is HQET. There's SCET. And there's, chiral perturbation theory, right? Those are all effective field theories of SCET, all of which enjoy the same degrees of freedom in the exact same symmetries. Yeah, if I don't have power counting. In order to select out one of these, I need power counting. And once I have power counting, there's going to be some ground states. So that which I don't want to depart too far away from. And the allowed departures. So how far away I'm allowed to actually go from that ground state, which would be dependent upon what I'm actually measuring. Once I have my power counting, then I'll select out one of these particular theories that I wrote down as being the actual object of interest. Because maybe my ground state is bottomonium, in which case I want to be using NRQCD. Or maybe it's just some B meson, in which case I want to be using HQET. So what are our degrees of freedom in QCD? Well, that's simple. It's quarks. So I'll have some field operators. And these are flavor indices here. So F is up, down, strange charm, bottom, dot, dot, dot. And gluons. And for gluons, I'm actually only going to write down the covariant derivative for right now. Because it is the covariant derivative that has the proper gauge transformations. Now, what's the major freedom that I want? Not freedom, symmetries. What is the major symmetries that I want? Well, the one that's most important for our construction of SCET is just going to be gauge symmetry. And, you know, of course, there's going to be smart Alecs out there that tell me that gauge symmetries aren't really symmetries. That they're redundancies, but whatever. What are the allowed, what are these gauge symmetries? Well, the gauge symmetry means I could take one of these fields, say my quark field. I perform a gauge transformation where I rotate my quark field at each point in space-time by some matrix U. U is in SUN C and fundamental rep. From my covariant derivative, I can form my field strength operator. And my field strength operator will also transform under those gauge transformations. I'll make it fancy U. The fancy U is also a member of SUNC. In fact, it is the same member of SUNC as what I had for my quark field. However, I've now mapped it to the edgement. How do I map between the two? Well, in case you don't know, U equals, let's see if I can. That'll give you the map between the two. The fancy U is related to my fundamental U by just sticking in TA, which right here are my fundamental generators. Now, if we've all made it through the second semester of quantum field theory, hopefully you've seen particular equations like this before. And so you sort of basically know what I'm talking about when I say gauge symmetries and how the fields transform, yada, yada, yada. The other thing that you would learn about in your second semester of quantum field theory is that based on these, I can form particular invariants. For instance, I could take the trace of the gauge indices of my F mu nu, and this would be gauge invariant. I could also form psi f bar of X, psi f. This would be gauge invariant because my psi f bar transforms into anti-fundamental because it's basically just the dagger of whatever my psi was. And so these would be two invariants that I could form if I'm interested in QCD. And if I'm interested in just the action of QCD, then thinking about these two types of invariants is all that I need because I like my actions to be nice and local, and these are local invariants. However, in general, local invariants are insufficient to do anything useful when it comes to QCD. So the first order of business is that the list of invariants that I can write down is not exhausted by these local invariants, right? I need a much bigger list of invariants that transform under my, that do not transform under my gauge group, which will be these non-local invariants.
So are you gonna argue that the Lagrangian, everyone writes down, every professor writes down QFT and almost all the other invariants is really, can be argued to be small?
Yeah, in some sense, yes, right?
I mean,
You need a power counting in order to justify that particular action. that you
So
wrote
you
down.
would say that, yeah, this is QCD as written down in standard field theory course is an EFT.
Well, I mean, it is an EFT, that I'm convinced. It's turtles all the way down.
It was. It's turtle.
It's turtles all the way down. We're just EFTs on EFTs. There is no fundamental theory. That's what the LHC is proving to us.
Okay, all right. But I remember this, I sort of thought about it.
Yeah. It's not just.
One of the most unsatisfying things in QFT when I was a graduate student was there were all these invariants.
Yeah.
And they wrote down this one.
Yeah.
And when you argue that the better way to explain that is to say we have these ground states, these fields.
Yeah, so when I write down normal QCD, then what is the ground state that I'm thinking about? I'm thinking about a perturbative ground state where there are no gluon or quark fluctuations, right? And now I'm going to start putting gluon and quark fluctuations in momentum space on top of that. And you can quickly convince yourself that the action that people do write down, which is just the ones out of these local invariants, would be the best one, would be the leading power ones, according to a power counting that I could assign there. But it's not just building an action that I need these invariants, right? And I mentioned this earlier. Where is it? I need my invariants because those are the things that can be physically measured. And that's what I should express the dynamics in terms of. So we're going to find things that are just non-local in QCD. For instance, bottomonium is non-local in QCD. I have two bottom quarks that are pretty close to each other, but they're not on top of each other. So if I really wanted to describe that, I'm going to need some non-local invariant because I can observe it in nature. And the system itself is non-local, right? Same with a pion. I have an up and a down quark of some particular flavor or anti-flavor. And they're not right next to each other, not on top of each other. I need a non-local invariant in order to describe what I can see in my experiment, which is pions, right? So it's not just building the action, but it's also, I need to build a whole host of different invariants other than these local ones because QCD presents us in nature with non-local objects that we wish to describe. And anything physically measured can't be dependent upon my gauge. Symmetry. So we're going to go beyond QFT too. And we're going to start building non-local invariants. And you'll quickly see that the space of non-local invariants that I can build in QCD is infinite. Now, how do I make something non-local? Up till now, I've written down these local operators, right? They're just creation and annihilation operators or covariant derivatives acting at a particular space-time point. And I want to write down something non-local. Well, for something to be non-local, I can always start at a point and I can start moving around. And now I've built for you some non-local object because I started at a point and I started moving around. And I want this non-local object that I've built to have sort of nice transformation properties under my gauge transformation. In other words, I want it to transform, say, like this psi bar field or that psi field that I wrote down earlier. In particular,
What about Lorentz symmetry for non-local operators?
that's a good question. You contract up your indices, right? I mean, I can contract my indices between two objects that are very far apart from each other, right? And because my Lorentz symmetry is a global symmetry, it acts everywhere at every point identically, right? So I can have an operator over here and I have an operator over here. And if I perform a Lorentz transformation, then the displacement between the two are the same, right? So if I've contracted up the indices, I'm not worried about it. If I'm in general relativity, then I start getting real worried, right? But we're not in general relativity because we're nukes.
What?
We're nukes.
Oh, sorry.
But yeah, so since Lorentz symmetry is a global symmetry of my system, then I'm not worried about contracting up some Lorentz index here with some Lorentz index that's sitting over here. So what tells me how to move something around? Derivatives. In particular, what I really want to do is take a gauge transformation that I would like to perform at this particular point and move it all the way to this point and perform it there instead. So here's my operator that I want to drag around, phi of x. And then we'll just assume that phi of x transforms in the fundamental for right now. But I'm going to make an additional requirement that for some initial displacement, so I'll be right here, here's x. I'm going to make some displacement in the direction dx, that my operator does not change covariantly. So this is the covariant derivative. So this is what I'm going to assume. Off of this assumption, I'm going to start repeating that assumption over and over and over and over again, because if I have a bunch of displacements, I can eventually build up a path. And that will show us how to move the gauge transformation at this point x to some point y. Now, if I'm actually going to move this operator, then I actually want to look at the point x plus dx. And if I expand that out, oh, no, that's wrong. Not a covariant derivative. It's a regular derivative, right? Because dx is small and then it more higher order terms. But the important point is that I've assumed that my covariant derivative along this particular direction is 0. And if we recall what my covariant derivative is, it's my normal derivative plus the action of my gauge field. Which means in this term right here, I can get rid of my normal derivative and I can put my gauge field in there instead.
This is just like a gauge theory version of parallel transport.
Yep, that's what I'm doing. Now, everyone should recognize that 1 minus some small quantity is actually an exponential. And now I can look at the gauge transformation properties of phi x plus dx. Now we know that.
What were you able to put the question before there? GA,
Because I made this assumption,
you're doing it in such a way that, okay.
right? I'm just assuming that this object phi, I'm trying to construct what phi is right now, right?
Okay.
And so since I'm trying to construct something, I can make an assumption about it and see where that assumption can go. Since
So
I'm
I
trying to build.
stepped out
Yeah.
for a second. I missed my assumption.
But yeah, it's really this particular assumption that I've made that's allowing me to do this.
So this is still a very small transmission.
Yeah, very, very small. Very small. I haven't really gone anywhere.
So, but you're arguing that all fraction terms
Are small, because I can keep taking dx as small as I want.
I agree on that. Is there an argument that says you can actually exponentially alter it? Or is it just an approximation?
It's just an approximation, right?
They're equal to terms. Right?
Yeah.
It drops off fast enough.
No, I know the argument. I've always wondered about this summation of it, and then you integrate.
Well, eventually I'm going to build up an interval and I'll have my normal
Right.
magical object that I don't want to give away yet.
So you could just write down the identity I partial is equal to minus GAX.
Yeah.
Right? And that's really all you're doing.
Yeah. So now we should examine what happens with our gauge transformations, right? Because that's what we're interested in. So 5x plus dx maps to u of x plus dx 5x plus dx, right? But this object here (5x). And when I perform my gauge transformation, I should also recall that phi of x goes to u of x 5x. But when I look in this expression, there's no u of x there, which tells me that this object that I constructed under a gauge transformation has to transform like this. In other words, it's moved my gauge transformation at x to a gauge transformation at x plus d of x. Now, what do? Well, I want to move a long distance. So I write down a whole bunch of these. And the reason why I did it this way is to motivate why there's going to be a path order. That's really the heart of behind this derivation, right? There's, I could have just given you the object and said, look, this has the transformations I want. But I'm trying to motivate why there is a path order. Before, up until some final movement, dxk gets me to where I want to be. So here's x initial, here's x final. Now, how do I move my transformation? Well, I think about, it's u. I'll think about an S that's going to depend on some path gamma. So here's my gamma. It's going to move me to point xf from the point xi. And what is this object? It's going to be the limit as all my differential steps. I have an infinite, I want an infinite number of them. So all my differential steps have to strict to 0. So k is going to go into infinity. I guess I'll write it this way. There'll be e to the minus I g dx k dot a x plus my displacement up to that point. So delta k equals sum L equals 1 to k minus 1 of dx L, right? Because that tells me how I moved along my path. So that's the first term. So that's what's happening at this point. Then I need my next term, which is happening at this point, e to the minus g dx k minus 1 a xi, sorry, there should have been an I there, plus delta k minus 1 dot 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 up to I minus g dx1 dotted into a x1 or xi. And what's important is that the order in which I wrote this, I have to keep. I'm not allowed to change that ordering because A is a matrix in SUNC and it doesn't commute. So I'm not allowed to change this particular ordering. Now, when we actually write down S gamma x to f x to I, and you can prove to yourself based on this property that I wrote down here, that this S, when I do a gauge transformation, will transform as U xf S gamma x f xi U dagger xi. In other words, I've moved my gauge transformation from xi all the way to xf. And that's just using this particular formula over and over again in this particular formula. So I've moved my gauge transformation from one spot to another spot. This object we call a Wilson line. Unless you're Russian, in which case you might call it Polyakov line. But people try to be fair and they only do it when you're talking about Euclidean space. Because anything that Wilson did, Polyakov did better. Wait, no, sorry. Anything that Polyakov did, Wilson did better. Some Cold War going on there. That's a Wilson line. And normally we don't write it this way, right? But I wrote it this way to motivate for you why the object that we actually write down is what we call a path-ordered exponential. Normally what people would write is this object. And in the case, and this will be the case that we'll be most interested in, that my squiggly line is actually just a vector, then this particular form actually becomes very useful. But we'll get to that in a little bit. Now, I haven't built an invariant yet, right? I've just built something that moves a gauge transformation from one point to another point.
Do you want to put a 5 on the left-hand side of that? Or does it matter? I mean, on the SCET, where you form the translation.
Oh, I mean, this would be S prime, right?
Right.
So that's why I always wrote an arrow instead of an equal sign.
Okay.
Because it's
Yeah. Sorry, I didn't.
yeah.
I thought that was.
No. I completely agree with you. If it was an equal sign, I should have written a prime. But this is a replacement rule in mathematics. So it's an arrow. But now I can build non-local invariants. For instance, I can build for myself a pion of some sort. And now we see we have a non-local gauge invariant object. But of course, even this particular non-local gauge invariant object I have an infinite dimensional possibilities of it, right? Because any path gamma that I want to choose will give me some non-local gauge invariant object, right? So I still haven't done anything useful yet. Just like when I started writing down my invariants for jelly and I wrote down my most general jelly action that I could possibly write down, I didn't do anything useful. We needed something extra in order to start limiting the space of possibilities that we have. And I guess we started at 10:10, right? Is this where we take a break? 10:15. Okay. At 10:15. So now I'm going to spend a little bit more time on these Wilson lines because there's a particular type of Wilson line that we're going to need for the construction of soft collinear effective field theory, or really anytime you want to sit down and do some sort of factorization. And what is this particular type of Wilson line that we're going to be most interested in? It's Wilson lines, which are just straight line segments. And the reason why that's nice is because they're completely specified by some Lorentz vector v, which just tells me how to go from xi to xv. That's just the Lorentz vector that points from xi to xv. And I can always, and depending on what v is, I could have null lines, I can have space-like lines, I can have time-like lines, and I could also make these small if I want to. So I could just have some number here, say alpha. And so depending on the displacement between xi and xf, I'll get different types of Wilson lines. But right now, v is just some fixed Lorentz vector. And if I have a fixed Lorentz vector, then I'll use this notation. I'll just specify the vector, not the entire path, because the path is just moving along that vector and just keep moving along that vector. What's also important, actually, I'll write it this way. This will be a better notation. I'll write down just my starting point and the amount of time that it takes me to get to xf. So what is that t? Well, that t is xi plus vt. So you tell me what xi is and xf, and what v is, that tells me what t needs to be. It's just the amount of time it takes me to move along that vector till, yeah.
So this vector is always spatial, are you writing it?
It could be null. Time, this is time in quotation marks. This is parameterization of my path, right? That's what it really is. It's just a parameterization of my
It's
path.
linear in 4 space.
Yes. Sorry, no, don't want to do that. Confusing myself. Okay, sorry, my handwriting is so big. Let me try that again. There, fit it all on. So what is this path ordered exponential? Well, earlier when I wrote down gamma, it's kind of hard to understand what that path ordered exponential meant. But here I can actually write down a very simple expansion for this object completely in terms of intervals. So you don't have to use that weird expression I wrote up where I'm multiplying all these exponentials together. And really, by path ordered, you should just think, oh, path ordered, time ordered, that sounds like the same thing. So it should be sort of a very similar type of interval that I would write down. I'll just write down the first two terms for you. Now, you might be tempted to try to commute these two past each other because they're at different space-time points, right? And local operators that are at different space-time points should commute. No, do not do that. Remember, we had to multiply the gauge matrix against itself each time. So I'm actually not allowed to commute these two past themselves because of the gauge group indices. A is a matrix in whatever representation my Wilson line needs to sit in. So what this A might actually mean, say I had an adjoint, no, not an adjoint, say I had a fundamental Wilson line. Then really that A is going to be some adjoint index tied to my generators of my Lorentz group in the fundamental representation. And I really should have some indices here, ij, so that this object up here would have actually had those indices ij, but I didn't write them down earlier. Let me write it this way. And then this term here, what if the structure is going to look like? It'll be A, T, A, I, K, A, B, T, K, J. So the hidden fundamental matrix C that would be here and the hidden fundamental matrix C that would be here are actually multiplying each other. And I should make it clear that I'm not allowed to commute those two without using my Lie algebra, Lie algebra, I should say.
This question, what about the subscript I on those x's? Those really necessary?
But they're not really necessary.
In a sense, right? It's a different.
Yeah. I mean, I could erase them
I don't know
all.
if they're like misleading in that last expression, just because it's really the same point. Right? It's like I just don't really understand if it's necessary.
All right. And then I could keep going. Where I keep having these nested intervals, and I just have to keep track of the order in which these A matrices are appearing with each other. And I'm not allowed to commute them because they're matrices multiplying each other in my group space. So now is it a break?
That's perfect.
Yeah.
So let's say you build this on local. You build these invariants that are on local and you write down an effective Lagrange. PCB, we don't have these gauge lengths in
Yeah,
So I want to give you.
in SCET, we do have these constraints with the Lagrangian.
So are you building not PCB, you're building PCB?
Well, right now, all I'm doing is
Okay.
trying to give you a recipe to build the most general invariant that's not topological in SCET. I haven't exhausted the list of invariants that we could build because I'm not talking about topological invariants, right? Which are not going to be captured by these Wilson line structures, at least in 4+1 dimensions, not 3+1 dimensions. I guess if you're in 2+1 Wilson lines could be topological. But
I'm just thinking, what distinguishes what you're doing with fundamental fields?
I'm not even doing SCET yet. I'm just,
No, I know you're,
Yes.
no, in fact, I see you building the one in PCB,
yeah,
and because of the fundamental fields, and you're perturbing around the states, and it seems to me that the next logical step would be to say that your Lagrangian for PCB has these statements.
until I have a power counting,
Okay.
I don't know what to write down for my Lagrangian. That would be my,
It's you're gonna do a power counting that tells you your leading order Lagrangian and that power counting should have these things in it.
yeah.
You have, 25 minutes in your
Oh, I have 25 more minutes in my lecture. So I thought we had a coffee break right now.
You started at 9:15. So you have an hour and a half, and then we're supposed to have half an hour coffee, but we'll do a 15-minute coffee. We started 15 minutes late, so you still have 15 minutes. 25 minutes, sorry. Yeah.
All right.
Would you can split between?
I was
reading and discussion.
So my invariants. Now that I've constructed my Wilson line, I'm going to touch on a subject. Wow, it straightened it for me. We'll draw some choppy waters. This will be a point that is contentious in the literature. Here be dragons.
Oh, it's a factorized step diagram.
So there's my caveat, here be dragons. When I'm going to be doing factorization for hard scatter, there's a particular type of Wilson line I'm going to be interested in. And that's one where my XF, my endpoint, is at infinity. And what is at infinity? Well, there be dragons. So I can always think about some object where, let's see if I can remain consistent with my notation, xt, x, infinity. Now, when I do my gauge transformations on my Wilson line, right? It behaves like, where's my equation? It behaves like this, right? I have my gauge transformation at xf, and then I have my gauge transformation at xi. When I've taken t to infinity, there are no gauge transformations at infinity, and don't you tell me otherwise. Okay, yes, there can be gauge transformations at infinity, but only if we care about non-local gauges like the light point gauge or axial gauge. But that's what I mean by there be dragons. At infinity, I'm going to make an assumption that there are no gauge transformations at infinity. So once I've dragged my XF off to infinity, I don't have to do anything with that particular index to get rid of its gauge transformation properties. It's just not going to transform there. Now, like I said, this is a controversial statement. And there's interesting physics here. What are those interesting physics? Well, you know, you might see words thrown around like Glauber's, transverse Wilson lines. So on, but we're not going to worry about it. So for this infinite, semi-infinite Wilson line that I've written down, I only have gauge transformations at the point where I start. So where does this guy transform to? Now that's interesting, because now I can start building invariants built only out of Wilson lines, where there are no operators. So earlier, when I wanted to build a pion, right, I was like, okay, well, I have some pion field at xi and some displacement away. I'll have not pion, sorry. I'll have some quark field at xi and some distance away. I'll have some quark field at xf. And then there'll be some gauge link between the two that, you know, I can imagine is describing the flux between these two objects. But what all I really care about is I have an invariant object under gauge transformations. And I know that, you know, the two things aren't going to be much further away from each other than whatever is the width of a pion. Here, I don't have to put down any field operators at all, right? I can get rid of this gauge transformation by just having another Wilson line meet there. That follows its own path out to infinity. And now I have a gauge invariant object.
So can you make a statement that, or that two quarks are close to each other, you know, depending on time, for example, this link is short.
Yes.
And here, you're just exploiting that if you put a gauge, that allow you to form this object.
That's gauge invariant. Yeah. And this object in hard scattering factorization will play an important role. In particular, if I'm interested in, say, factorizing amplitudes, then I might put some sort of time ordering around that also. And I might start thinking of matrix elements of the time ordered product of these particular Wilson lines as reproducing for me some type of amplitude. Now, if you do want to get into sort of this issue of gauge transformations at infinity and whatnot, I think I'm disorganized, am I? I wrote down the paper number. Otherwise, nausea will come after me. I didn't write down the paper number. Anyhow, I'll post it in. I'll post a whole bunch of papers for my entire talk in the Slack. But there are papers in SCET that deal with these gauge transfer with this issue of how you actually tie up the gauge transformations at infinity. And there's also corresponding papers in the QCD literature. PQCD, more traditional PQCD literature. And this statement in some sense is going to be true as long as I restrict myself to covariant gauges. I can guarantee that to be true. So there's a large class of gauge transformations for which that would be true. So now I've taught you the degrees of freedom. I've taught you how to build invariants, but we can't do anything useful yet because we don't have a power count. Now, in order to have a power counting, we needed a ground state and the allowed fluctuations. And these fluctuations are going to be weak. In other words, they're not going to really change what I call my ground state to be. Since we're doing T&D physics, the particular type of ground states that we're going to be interested in are sort of Born scattering configurations, right? So what's a simple example to start thinking about? Well, it's an example that got my thesis started. We're going to think about the Higgs decaying to 2 gluons. And I'm going to call this my ground state. Now, I can go and, this is going to be mediated by some operator that looks like HF squared. Dot, 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 dot. Here's my Feynman diagram. I'm going to scatter to these states with some particular polarization and some momentum, Q1, Q2. This is going to give me some amplitude. Right now, we're only going to be worried about the tree level amplitude. And it's going to depend on, we'll say 1A to B. And when I write down the 1, I really mean Q1, epsilon 1, both the polarization and the momentum. And this thing is going to be some normalizing factor. Q1 dot Q2, epsilon 1 dot epsilon 2, minus epsilon 1 dot Q2, epsilon 2 dot Q1. And, oh my gosh, I write way too big. Delta AB. There. Hopefully that's legible. So this is my ground state. This is the state that I'm interested in. It's just my Higgs decaying to 2 gluons and only 2 gluons. Now, what are the allowed fluctuations around that? Well, I could consider my Higgs decaying to those 2 hard gluons plus a whole bunch more gluons. And as long as these are sufficiently soft, or collinear. Collinear to what? Collinear to my Q1 and Q2. And by sufficiently soft, I mean they're just not carrying very much energy at all, and they could be anywhere in my scattering process. Then this process will look essentially the same as this particular process. In other words, it'll only be a weak fluctuation around Higgs decaying to 2 gluons. These gluons that they decay to might have acquired a little bit of invariant mass if I drew a cone around them and asked what's all the radiation flying into that cone, but it wouldn't be very much. So this would have the same basic momentum configuration. Collinear in just the right way to preserve the total momentum Q1 and some small cone about my initial Q1. So inside that small cone, I can have any number of gluons that I care for. All of their momentum add up to approximately Q1, up to small corrections.
basically like 2 10 jets of gluon.
Yeah.
Is your ground state.
Yes. Well, really, my ground state is just 2 gluons. But my allowed fluctuations about my ground state are now these 2 cones with the arbitrary amount of gluons inside those cones, and anything soft can be anywhere outside of those cones.
Therefore, collinear by they have to be in the thing.
Yeah. So here's my Higgs at rest. There's cone 1, there's cone 2. I'm allowed soft radiation, and anything inside here, anything inside here. This has to be approximately Q1 when I sum PI, I in that cone. Right. And then same condition on the other side. And the size of my cone actually is going to, if I went far enough, would tell me what my power factor should be. But right now, we're going to leave it a little bit more fuzzy. So it's processes like this, which are my allowed fluctuations, right? If I go back to my example of the jelly, I had X, jelly at rest, everywhere at all times. Then I added plus pi, which is some small displacement around that X vector, right? My ground state is the Higgs decaying to 2 gluons. So that's my X vector in the jelly example. And now these particular types of configurations are my allowed fluctuations. And what do I want to do? I want to build an operator which describes all 2-jet Higgs decays.
By jets, you mean jets where you can't distinguish between Q and some of them soft.
Yeah, they're all falling into the same parameter sum. Right. Now, to make my life easier, I'm going to do everything right now at the amplitude level. And I'm going to go through a procedure. Since we're building things from objects we know up, right? Normally, when you read an SCET paper, they'd be like, "Here are the rules," and now we derive everything. So right now we're going to go on the discovery journey for SCET, as opposed to sort of the top-down formulation of SCET, where here are the rules. Start using them. Eventually, you'll get comfortable enough. Your hands will be dirty enough that it will never wash off, right? That's normally how we in SCET operate. And in order to figure out what sort of operators that I should be looking at in order to interpolate sort of this arbitrary 2-jet state, let's first just think about what happens when I add one additional gluon. So now I have, I'll relabel things. I'll call this P1. So 1A. This guy will be P3. And there'll be other diagrams. Like so. Well, and I think that's all the diagrams you would have to worry about for this particular process. Now, I'm not going to go through the brutal exercise of actually writing out those diagrams and doing all those contractions. I'm going to make use of a fact that hopefully you've seen before. I could go through and I could do all this algebra, right, and write down that full expression of what this amplitude is, which will depend on P1 symmetry. See. But the first thing I'm going to investigate, and so right now I'm not doing any effective field theory, right? I'm just operating in full QCD. We have our Feynman rules from QFT2, right? I can plug those Feynman rules in here and I can do a whole bunch of algebra and I can calculate what this AT is, right? We could all go through this exercise and we would spend a day on it if we actually wanted to do it in gory detail. So this is all full QCD. Normal QCD that we've already learned. I'm going to take the limit that P3 is soft. Why do I want to take the limit P3 is soft? Because I want to understand the structure of these types of configurations where I'm going to have arbitrary amount of additional radiation on top of my two hard gluons that the Higgs is decaying to. I know that if I take P3 soft, then I should get back to essentially something that looks very similar to my ground state that I wound up with, that I want to preserve. In an invariant language, what does P3 soft mean? Well, it means both of these quantities are going to be much, much less than 1. Both of them. And as that happens, my P1 is going to approach Q1, and my P2 is going to approach Q2. Because definitely, if I want to stay close to the configuration of Q1 and Q2, my two initial hard gluons, then I definitely want to demand that this is always true whenever I'm doing a deformation, up to some small corrections. In fact, you could demand it to be exact. You really need to. So when I say soft, I mean all of this. Now, we can go through full QCD, we can calculate what that tree level scattering is to 3 gluons, right? And once we had that in our pocket, we could then just do that expansion of P3 to be soft. I'm just going to write down the answer because I don't want to actually do that calculation. So this is dependent on
Yeah, a couple minutes left.
Should say something to fill the void of silence. All right, hopefully that's legible.
So what is it? Is this times I?
Yeah, times, sorry. Yeah, so this part right here is multiplied to that part. So F are my structure constants for my gauge group. It's kind of nice. I'm seeing my original configuration back, right? This is being multiplied by the tree level amplitude of my H going to just these two gluons. But now it's being multiplied by this weird factor that I wrote down, which is my iconal factor. Now, right now, I don't know anything about factorization. I'm pretending, right? What we did is I used my full QCD Feynman rules to calculate my 3-point scattering, and then I just expanded it, and then I got this particular answer down. And this answer is going to be valid up to things that are going roughly as whatever the energy of P3 is. Just do that. Up to some corrections that are in the energy of P3.
So,
Yes.
so you're saying these denominators are
Yeah.
Yeah. Okay.
Yeah. Right. And that's what I would just discover. So now,
Does that mean that if you were to draw a Feynman back, can you scroll back up a second? Where you have the- Yeah, right there. So does that mean that, for example, in the top diagram, you have some icon on?
yeah, you would find this as icon, this particular propagator here is iconalized. Yeah.
It's an icon for Gluon.
Yeah.
It's got the epsilon.
Well, right now everything's at tree level, so I am just forgetting about my I epsilons.
Okay.
But no, there should be an I epsilon there. I completely agree with you. So,
So that would just be bounded as well.
Yeah.
Okay.
and if I was starting to do loop integrals, then I better pay attention to that particular I epsilon. But right now, since I'm just doing real radiation, I'm not. Yeah, yeah.
Okay. Yeah, let's take a break there and we'll continue at 2:11:05. Coffee for just under 20 minutes and then we'll continue.